Okay, so in our number 3 from worksheet 7.3, we have a line given that goes through 0, 2, and 4, 0. And using the coordinate axes as our other two boundaries, we're going to end up with a triangular shape here. And the question here is to find the volume of a solid where each cross-sectional slice is made perpendicular to the y-axis. So if I were to draw my slice, we have a horizontal slice, which ultimately means we're going to be dealing with y values or y equations, if you will. It's a horizontal slice, no matter whether we're dealing with a solid in a plane or whether we're dealing with a revolutionary solid, whatever the case may be. Right? And bottom line here is this slice is an isosceles triangle with the hypotenuse here as the base. And so if we were to draw a picture of this kind of in 3 dimensions, we might have something that looks like this, where that slice is coming out of the paper at us as an isosceles triangle. So keep in mind, isosceles means those two lines would be equal to each other, those two side lengths. And again, the hypotenuse is on the piece of paper. Okay, so it's coming out at us with the two legs coming out. Hypotenuse is on the paper. And so bottom line here is if we're going to try to find an equation that will give us the answer to this, which ultimately will end up being an integral, we need to start out with, first of all, if we have a triangle that we're trying to find the area of, we start out with our most basic formula. Area equals half times base times height. Now with an isosceles triangle, we know that in an isosceles triangle, the base and the height are going to be equal to each other. Okay? It's just the two legs. Okay? And so the ultimate decision that we need to make is how are we going to find the base and the height here for this particular triangle. Well, we also know that with an isosceles straight triangle that it's 45, 45, 90, so we know there's a relationship between the hypotenuse and the base and the height. So if we can write the base and the height in terms of y here, which is going to be related to our function, then we can ultimately set up an integral and find the area or find the volume of the entire shape. So bottom line here is that again in this picture, if we knew what this hypotenuse was, then that would give us some insight as to what the two legs are. So ultimately the hypotenuse here is going to be, if we write this equation, the equation was x plus 2y equals 4. So if we solve that, we're going to get 4 minus 2y would be our x. So ultimately wherever that slice is in the region, okay, the x value here, in other words the length of that hypotenuse is going to be 4 minus 2y. Fair enough? So, with that said, if I were to draw that on my two-dimensional shape over here, if this is 4 minus 2y right there, if that's the hypotenuse of an isosceles right triangle, the question is how do I get back to the two legs? Well, I know that if I have two legs, I multiply by radical 2 to get the hypotenuse. So to get back from the hypotenuse to the legs, instead of multiplying by radical 2, we'll divide by radical 2. So ultimately here, what's my b? It's 4 minus 2y over radical 2. And you can rationalize that right now if you want to. You don't really need to, but you can if you want. It's up to you, but I would just leave it like that for the time being. Which, but ultimately, again, that is our b value here. Now, knowing that, then we can now write an equation for our area of the triangle that I have drawn on my paper right here for this triangle. Okay, it's going to be the base, which we just figured out is 4 minus 2y over radical 2. And then what about the height? Keeping in mind that in an isosceles right triangle, the base and the height are what? They're the same. So it'd be just 4 minus 2y again over radical 2.
The base is the hypotenuse.
It says the hypotenuse is in the base of the region, though.
Yeah, so then the base of the triangle is
So keep in mind this dimension right here on my two-dimensional is this right here. Oh, it doesn't need to be split because it's a right triangle. The base and the height are perpendicular to each other in any triangle. So any right triangle, the two legs are going to be the base and the height. Remember, the key issue with base and height with triangles is that they're perpendicular to each other. That tells us that they are the base and the height. So that's why the hypotenuse is not the height or the base. Okay? If you wanted to make that the base, you could make this more complicated and turn it on its side and then draw a triangle in between them. And then you're going to be dealing with a 45, 22.5, it's ultimately going to be much more complicated. Okay? So just note that since it's a right triangle, the base and the height are the two legs that are perpendicular to each other. Okay? That makes it much easier to deal with. Alright, so with that then, our area expression, if we simplify it, we're going to have 4 minus 2y all squared on the top. And on the bottom we're going to have 2. We got radical 2 times radical 2 would be 2 times 2. Nope, I lied. 4. Sorry. 4 on the bottom. 2 here because of these two, and then another 2 would be 4 all total. So that would be our expression for the area of that one triangle. So bottom line is, what do I do to find the volume of the entire solid? In other words, take all the triangles and put them together. We're going to write an integral here, and that's going to be our integrand, 4 minus 2y squared over 4 dy. And then we're going to go in the y direction, 0 to 2. And that right there should give us our integral. And so, ultimately, in our drawing and labeling, we've drawn the label here for part A, and labeled is our 0, 2, and our 4, 0. It says draw and label a slice that's made perpendicular to the y-axis. That's what I've done here. Here's my slice. Here's my slice in 2 dimensions. It says give the area of the cross-section of each solid. And remember, the area of each cross-section is this expression right here, which simplified is this. True? So that would be our answer for part C. The volume of one slice would actually just be the integrand times dy times the thickness. That makes it a volume. Right? So that would be your answer for part D. And then part E would be give the volume of the solid as a definite integral. Now put our 0, 2 on there. That makes it the definite integral. That's the volume of the entire solid. And then finally the answer, of course, is just a calculator problem. And we do it with our Math 9 command. And we get 0.25 times 4 minus 2x all squared, x comma 0, 2. I typed in there right, correct? That's good. Get 2 2/3, which of course as a fraction is 8/3. And so ultimately we get 8/3 as our result. I believe that's what it said on the overhead, right? Questions on any parts of that one? Okay, we're going to go next then to our, we're going to do practice quiz first, and then we'll go back to our 7.1 through 7.5 worksheets. So in practice quiz, I'm going to read the answers to you, and then we'll do questions from it. So the multiple choice answers should be as follows. Should be 1 should be C, 2 is A, 3 is D, 4 is B, 5 is A, 6 is C, and 7 is B. Any 7 out of 7s? A. 6 out of 7? 5 out of 7? Getting there. Alright, where should we start? Jeff?
2.
Okay, number 2 we have, it says the graph given to us here. It's like a line segment, it goes from 0, 2 to 2, 0. And then it goes down to 3, negative 1. Continues on there. And then it goes horizontal, past 4 and 5. Alright, so it says here that this is the graph of velocity of the particle on the x-axis is given. So the particle starts at x equals 4 when time is 0, and find the particle's position at the end of the trip, which is time 5. So ultimately time 5 is the end of the trip here. Alright, so given this being our velocity equation, and we want to know where is the particle at the end, all we're after here is what is the displacement then. Okay. So we know that this right here is a 2 by 2 triangle. So its area then would be 1/2 times 2 times 2, which would be 2. This right here, this triangle right here, if we split this up into parts, that triangle is a 1 by 1, so that would be a half, but ultimately it would qualify as negative 1/2 since it's below the x-axis. And this would be a 2 by 1 or 2 rectangle. but again, it's below, so it would be negative. So ultimately, how much position did this thing gain? Well, it gained 2. Think about where it would be. Just talk to yourself through the problem. You're already keeping in mind that x equals 4 when time is 0. So let's just say, for argument's sake, at the next key point here, which is time 2, where would we be at time 2? We were at 4, we gained 2, so now we're at what? Now we're at 6. Okay? And then at time 3, we gained a negative 1/2. That means we went backwards a half. So now we're at x equals what? 5.5. And then finally at time 5, what did we gain? Another negative 2. So where are we now? X equals what? X equals 3.5. So where are we at the end of the trip? We're at position 3.5. Okay. Now, does that give us the total distance traveled? No, but that's not what we're after. We're not after the total distance. We're after the position at a particular time. So in other words, we take our initial position, which is position 4, and we add our total displacement. Okay? Our displacement is really just negative 1/2, isn't it? These two cancel each other out. We got negative 1/2 as our total displacement. So ultimately, where are we from where we started? We're a half unit to the left in this case, because we're moving along the x-axis, it says. So half unit to the left of where we started, 3.5. Questions? Very important problem and very important concept that we need to make sure that we can do that without even blinking an eye. Okay? In that packet that I gave you yesterday, that motion packet, got lots more problems just like that in there that we're going to continue to practice on, because these are very good AP type problems that you'll see on the AP test for sure. What else? All right. And number 3. We have a spring, and we learned that the spring constant, when we deal with spring is always going to be force and distance are going to be related by this Hooke's law. And it says it requires a force of 10 newtons to stretch a spring 8 centimeters beyond its natural length. So if it takes 10 newtons to go 8 centimeters, then ultimately we're going to get 5/4 to be our K here. And so for our particular spring, our 5/4 X is the equation for our force for this particular spring. So this is the force equation for our spring. Okay. So bottom line is it says how much work should be done to stretch the spring from its natural length to 12 centimeters beyond its natural length. Okay? And ultimately, work done is an integral of a force function. And so with that said, our work done is going to be from 0 to 12, natural length being 0, 12 being where we want to stretch it to. And our force equation is 5/4 x dx. So that's going to be our setup here to determine how much work is done. So if we do 5/4 times x squared over 2, we get 5x squared over 8, and we're evaluating that on 0 and 12. And so if we put a 12 in there, we're going to get 12 squared, which is 144, times 5. And whether it's on the calculator part or not, we'll use it for the time being here. And then if we divide that by 8, we get 90. Okay. All right. And then ultimately here, the units are important here because we have a force equation. Okay. And our force equation, okay, force is measured in newtons here. And it's measured in, the x is measured in centimeters. So keep in mind, if we have this force curve that we're drawing here that's measured in newtons, and we have our curve that's measured in centimeters, we know it's a line that goes to the origin. That's essentially our picture here. If we were to find the area of rectangles underneath there, we're going to be multiplying y units times x units like normal, and we're going to get what for our units then? Newton centimeters. And that's why it's 90 Newton centimeters. Okay. Because what we found by this integral is the area under this curve right here, which is our newtons versus centimeters curve. So therefore, our units for the area underneath it will be newtons times centimeters, or Newton centimeters. Okay. Questions on number 3? What else? Good. 4? Okay, and number 4, if you had to take a look at that right away, what would you guess in terms of what kind of slice you'd want to make with that region? And looking at the equations that were given. and it's going to have to be a horizontal slice. And if you look at it, if we just determine, you know, and bad art going here, but something like that, and then this thing comes through here like this. So ultimately something like that. But bottom line here is if we do a slice here, there's one function that's always on the right in that region, and there's one function that's always on the left. So bottom line, if we set up our integral, and our y coordinates here are 0 and 2. Nope, I lied. -1 and 2. Gotta have that bottom part too. So we're going up from -1 is the lowest y value in question here. If we're going from here, it's the whole region, not just the part that's above the x-axis. So the whole region. So it looks like -1 would be our lowest y value, highest y value being 2. So -1 to 2 is going to be our upper and lower limits. And then ultimately we need to make sure we recognize that we got to go right function minus left function. Can't be the other way around or we're going to get the opposite answer. Okay. So the right function here is going to be the cubic. So -y cubed plus 2y plus 4 minus the parabola is what's on the left hand side, which is y squared minus 2y. And one too many parentheses there, but that's alright. Put the whole thing in parentheses. And at that point, it becomes calculator problem. Unless it says solve it analytically. Okay. Just use calculator. So if we type that all in there, it should be whatever I said, which is letter B should be approximately 11 then. It says round to the nearest whole number. Again, key issue when we have this left and right horizontal slice is that we get the right function minus the left function. Always right minus left, just like in x, it's top minus bottom. Questions on number 4. What else? 6 is we got a base of a solid here. And it's between the line y equals 4. So we have 1, 2, 3, 4. That's going to be one of our boundaries. Line y equals 4. The parabola y equals x squared, which we know goes through 2, 4. So we have that as our another boundary. And it says the cross sections perpendicular to the x-axis are semicircles. Now here's one thing that we have to be careful with here. Is I only have half the region drawn here because did they say the y-axis is a boundary? So just the boundaries are the y equals x squared and y equals 4. So ultimately, wouldn't I have to carry it over here to -2, 4 also? And it doesn't say anything about any of the axes being boundaries, so that region enclosed by those two curves would be this whole entire thing. So keep that in mind. Alright, so with that said, it says that the cross sections perpendicular to the x-axis are semicircles. So we got slices that are perpendicular, and they come out of the paper at us as semicircles. Right? And so our job here is to write an expression here to find the volume of the solid. We need to write an expression for the area of that semicircle. Well, we know in general that the area of a semicircle is 1/2 pi r squared. Fair enough? And so with our information that we have, what is our r? What's that radius of that? Well, we know it's half of something. It's half of the difference between those two functions. So ultimately, if we did half of 4 minus x squared, and that would be our integrand. I'll write that a little bit bigger. So it's half of 4 minus x squared, because what does 4 minus x squared represent for this circle? 4 minus x squared is the diameter of that circle, isn't it? So we need half of it because we want just the radius of that circle. And then what are we going to do that whole thing? Square it. Okay. So the radius of that, diameter of that is the top function minus the bottom function. That would give us the diameter of the circle. Half of that diameter would be the radius, so that's our expression for the radius. And then from there, we can write an integral on -2 to 2. And we can take out the 1/2 pi, and we can write this as half. And we, of course, again, keeping in mind that we could simplify this before we actually did the integral. We could square the half, and we could square the parentheses, and so on. We could simplify it however we want. But bottom line is, if it doesn't say analytically, it's a calculator problem. So why bother doing all the simplifying? It's wasting time. True. So at this point, if we plug that into the integral, looks like should be letter C. So whatever we get should be should reduce to 64 pi over 15. So whatever we get here, multiply by a half pi. We get 64 pi over 15, which is letter C. But ultimately, that would be our setup. Anything else on this one before we move on? Alright, next. Number 7, we have a region that's bounded by the line y equals radical, or the curve y equals radical x. The line x minus 2, keep in mind x minus 2 down here, it's going to go up here and meet the curve at some point. So that's going to be our region. And y equals 0, keep in mind y equals 0 is the x-axis. Oh, it's the x-axis, y equals 0. And so we got y equals radical x, y equals x minus 2, and y equals 0. So ultimately we're looking at this shape right here. Not the bottom part, keep in mind, because it's y equals 0 is a boundary line here for us. So we'd be looking at this region. And ultimately we're finding the volume of the solid revolving. We want to revolve this around the x-axis. Okay? So keep in mind that we have two different ways that we could do this problem. One is you'll notice that top is always the radical x function, but the bottom here is the y-axis, whereas the bottom here is the other line. True? So our one thing we could do is we could split that into two separate parts and do two separate integrals here in x. Use vertical slices. And if we used a vertical slice here, we would get discs because it's right up to the line. Here, if we used a vertical slice in that, we'd get not discs, but washers. So our setup for that would be from, and again, this crosses the x-axis here at 2, of course. So we'd write an integral from 0 to 2, and that would just be pi times the radius here would be radical x squared dx. So that right there would give us the volume of this part just from 0 to 2. So it would be a washer problem, or a disc problem. And then if we add that to pi times 2 to 4, because both 4 gives us 2 in both of those equations. That intersection point right there is 4, 2. So if we went from 2 to 4, this time we'd have washers. So the outside radius here would be this distance, which is the radical x. And the inside radius is the line, which is the x minus 2. And so with that, ultimately after that, it's a calculator problem. And if we calculate both of those and add them together, we should get what I said, which is apparently letter B, 16 pi over 3. Anybody think of an alternate way that we could do this without having to write two integrals? Right?
Shells.
Yeah, if we did it with shells, we wouldn't have to use two integrals, would we? Because notice that the right side is always the line, the left side is always the square root. So if we did it with shells, keep in mind the setup with shells would be 0 to 2. We'd have 2 pi. Okay. If we were to make a horizontal slice in here, so we made that horizontal slice here, our distance between shell and revolving line would be this. This will be a busy picture when we get done with it, but bottom line is here. Remember, if I write a shell, it's going to be parallel to the revolving line, the x-axis. Okay, that distance right there is going to be y. Okay, and then the height of my shell is going to be the right function minus the left function. Now keep in mind that we'd have to solve those two. We have y equals x minus 2. So it'd be y plus 2 equals x would be the outside function. So y plus 2 would be that part, minus. And then the inside function was written as y equals radical x, so that would be y squared equals x. We'd have to write both of those in terms of y. And so our, again, right is the line, which is y plus 2. The left is the square function, the y squared function. So if we did that, we would have our integrand. And if we did both of these in our calculator, we'd both better get 16 pi over 3. Better get the same answer either way. Because we're getting the same region, same volume. So whether we set it up with discs and washers separated, or we set it up with one integral with shells, we're still going to get 16 pi over 3.
Why do we do that in y for that?
Well, because then we only have to write one integral, because we have the right is always the line, and the left is always the square root. Whereas with x, we have a different bottom here than we do here. So, and again, is one better than the other? Not No, they're both the same. They both give us the same answer. But we can't write one integral with the in x because our slice in here would have a different bottom as our slice here does.
Yeah.
So we have to have two separate integrals to do it in x. So a good problem because you can do it both ways, and it really involves all three methods, doesn't it? Huh?
So that just eliminates that experiment.
Well, that's good.
When you're doing the shell method and you use y,
Mm-hmm.
why do you use y?
Because this first part here, remember there's two parts to the shell method. There's three parts, 2 pi. And then this first part is always the distance between the shell and the revolving line. So here's the shell I drew, and here's the revolving line I drew here. How far apart are they throughout that whole region? They're how far apart? There's some arbitrary y.
Okay.
Depends on where I draw the shell, right? That's just that distance is just y.
The other one's the height.
And this is the height of the shell, which means the distance from here to here. And the height being horizontal in this particular case, but ultimately it's the height of the shell is going to be the distance from one end to the other, whether it's horizontal or vertical. Anything else on the practice quiz? All right, then I'm going to put up the answers for the next part here, which was our 7.1 through 7.5 worksheets. I believe we had 3 problems to do on that, right? I'm just going to show them on, actually I'll put them on the